Thank you for tuning in to another exciting episode. And we are going to be talking today about fossils and the fossil record. So, what we've learned up until this point is that when we look for fossils, we focus on sedimentary types of rocks. And what we also learned about sedimentary types of rocks is that them in themselves can represent environments of deposition. So, we use the example of sandstone, and sandstone can represent a beach environment. Limestone, a shallow marine environment. Shale, a deep marine environment. So when we think in terms of those sedimentary types of environments, what's interesting is that they give us a clue as to what was living in those environments. So another thing that we began to look at in laboratory was sedimentary structures. And so we looked at things like ripple marks and mud cracks, and those are also indicators of what the past environment used to be. In lecture, when we looked at some examples of limestone, we noticed that there were small clams, and that sometimes they're called brachiopods, and there's these corals that are called crinoids, and so those get trapped in the fossil record in those shallow marine environments. So it just gives us an indicator of kind of like a benchmark to start when we're classifying these different environments of deposition. So today what we're going to talk a little bit about is the history, because I love to do that. I love to give us a background of where the science was and where the science is going. One of the things that we'll keep in mind as we start to explore the fossil record is the idea of a geological gap. So this for sure speaks to the fossil record. So remember, the geologic gap was this idea that you're trying to fill in the pieces of the puzzle. So with the fossil record, we said, if the cat is pink, does that mean the cat has never been white? And so you're finding things in the fossil record, but you might not have found the cat that was white yet. It doesn't mean it didn't exist. It means that maybe we haven't found it yet. So it's a principle where we try not to exclude the parts that we have not yet discovered. On the screen, you have this fantastic fella, Leonardo da Vinci, and living 1452 to 1519. And you might think, like, why is he showing up in a geology class? We all know Leonardo da Vinci to be one of the greatest artists and inventors. You'll remember that he made the masterpiece, the Mona Lisa. But truly, he is one of the founding fathers on discovering scientific observation and as a major component of the scientific method, right? So identifying and asking questions and then observing to find out results and solving your hypothesis. Leonardo da Vinci has some fantastic drawings of the natural environment. So we can look to his records as being some of the very first to explain the fossil record in different parts of Italy. And you can find them on display throughout the country if you get a chance to visit. So Leonardo da Vinci making some very first observations about fossils, and that is going to be followed up by, once again, Nicholas Steno. I introduced the idea of Nicholas Steno when we started to talk about principles of stratigraphy, and we call him the father of modern stratigraphy, so the layers and organization of rocks and rock type. And we remember that he lived before the Huttonian Revolution, 1638 to 1686. And remember that his contribution to stratigraphy started and was initiated because he was digging ditches in the south of France for the purpose of some like irrigation. He was making some of these irrigation canals that became necessary. So Nicholas Steno, as he's digging those ditches, he's noticing the layers of the sediment, and he's asking questions about the organization of that sediment, but he's also asking questions about some fossils that he discovered. And so the first thing that he is asking is, when he's finding like these teeth that look like shark's teeth, he's like, how is this even possible? It looks like a shark's tooth, but is it really an organic remain? So is it really something that represents a past life? The next is, how in the world is a shark here in the first place, right? So when he's digging in soils and limestone substrates. So he's asking, why is this organic remain included into the rock layer itself? So essentially, how did the animals get into the rocks in the first place? The third question is, when did they get there? And so Nicholas Steno is standing in a ditch, and he's recognizing that there's no ocean environment, and this appears to be a remnant of something that looks like a shark. So he's asking, when did they get there, and how did the environment change so drastically? So he's considering a more lengthier time of the Earth, remembering that this is before the Hittonian Revolution, and so the age of the Earth is constrained to about 6,000 years old. And so it seems to him questionable that the climate could change so drastically over the course of such a short period of time. So he's challenging the age of the Earth also. And then when he's looking at the fossils, he's asking the question, well, how did they become preserved? Because when you look at a truly fossilized tooth, it has a different density. So it's much harder for fossil preservation practices that we'll talk about in the following lecture. So he just becomes curious, and remember, just like he did with the principles of stratigraphy, he began to write about fossils and the fossil record in addition. And so when he does that, he's making some comparisons between what modern shark teeth look like and these that appear to be much more dense and harder, and looking at the size of them and making some interesting comparisons. So my background is not in paleontology. A paleontologist is one that studies intently the fossils and fossilization record. But I have had some great experiences when I was a graduate student at University of Nebraska. So I'm over here on the picture of me in the right in the overalls. Talk about a throwback, right? And during the summers when I was a graduate student, I'd always volunteer to go on different expeditions, really just for the fun of it. And so one of my good colleagues, who now is at Columbia University, invited me along, and she was studying in the Nebraska sandhills out in the western part of Nebraska. She was studying these little creatures that were they're called pikas, and they're kind of in between like a ground squirrel and a rabbit. So they're very small, and much of the bones did not get preserved, but in this case too, pieces of these little animals' teeth were preserved. So it was like a little mammal. And so what we would have to do is we would dig and dig in the sandhills of Nebraska and get these buckets of sand, and you take them to a screen, and then you filter them, and you're looking for these tiny, tiny pieces of enamel from these creatures that lived during the Pleistocene, so about 1.8 million years ago. And what I learned is that it was very tedious, and lots of times you found nothing, and that just probably wasn't my cup of tea, right? I'm pretty much a bigger and more dynamic thinker. But it was fun being out in the field for sure. Stinking hot. We're talking Nebraska in June, July, and August, and of course there's no trees. So I had a fantastic tan at the end of it, but it kind of confirmed that paleontology wasn't probably for me. But I have also been on dig sites in western Nebraska where we found some major bones, and that's the picture that you see on the left. So there we're digging up a mosasaur, and you're familiar with a mosasaur because we talked about Alfred Wegener and him using that as an index fossil to confirm some of his ideas about continental drift. So that picture on the left there is us finding a piece of a mosasaur from the Cretaceous. So it can be really exciting when you find something big or a new discovery. So my question for you then, as we move forward, we can ask, what is a fossil? And so you're familiar with bones And truly, when we define what a fossil is, we can say that it's any type of evidence that suggests it was pre-existing life. So we do get very excited about bones, but we have to also consider other things that are living on the planet at different times. So that can include things like plants. And additionally, because a fossil is any type of recognizable life, we cannot deny the fact that things like footprints also get preserved into the fossil record, and that would be considered something that's very exciting and a contribution for us to determine how life changed and was evident on the planet during those times. And then in addition, we can consider the invertebrate record, and so we can consider things like worms that make burrows and leave what are called trace fossils in the fossil record. And so that gives us a clue as to the invertebrate type of life. So when we think of things like Jurassic Park maybe, or Jurassic World, and you see these landscapes, there is some pretty good indicators from the fossil records of what the plants might have looked like. So really, you're trying to use the fossil record to define the entire environment. So looking at the type of plants that were living, what the environmental conditions were as a result. And honestly, we might learn a bit more even about vertebrate life from looking at the footprint record, because we can tell something about how they migrated and moved. You're asking the question how fast they move. So similar to our pedometers, our Fitbits that we use at modern day, where we have to put in our height and our stride, we can figure those things out for dinosaurs. So we can figure out like how fast they move. So when people are recreating Jurassic Park, we do have some ideas about how quickly Velociraptor moved, or that they did move in packs, because we can look for those evidence in the fossil footprint record. So we learned a whole lot. It's really, really exciting to study. So as we move forward, we're going to talk about fossil preservation. So we're answering a question about how these living things on the planet become part and incorporated into the fossil record. And what I can tell you off the cuff is that it is very hard to become a fossil. So less than like 10% of life on the planet is going to be incorporated into the fossil record. Go ahead and write that down. So less than 10% of life that we see on the planet, and this is over geologic time, becomes incorporated into the fossil record. And so that really helps us again to think about the principle of geologic gap. So if the cat is pink, does that mean the cat has ever been white? We only are dealing with about 10% of life making it into the fossil record. And then remember, sometimes it can be like a needle in a haystack. So we're dealing with sedimentary types of environments and sedimentary rocks primarily. And so the conditions might not allow for preservation to happen, or it might be buried to some depth that we don't have accessibility to it, or it's not naturally accessible, like we'd have to dig in order to extract. So keeping that in mind, it makes the fossils that we do have pretty exciting, doesn't it? Okay, so when we talk about fossil preservation, we're going to outline 5 different things. And the first one is abundance of living population. So there's a big difference between the abundance of vertebrate life versus the abundance of invertebrate life. So when we begin to look at fossils in laboratory, one of the things that we're going to do is we're going to look at microfossils. And so microfossils are organisms that live in the water column, and they either make a calcareous or a siliceous shell, so a shell out of quartz, and that's what you're seeing over here on the picture to the left. These are microscopic images of something that's called a diatom. And so these range in, and they're beautiful. You can see the picture on the screen. These are living organisms. These are called diatoms, and they're microfossils. And so they make up the water column. So you can't visually see them, but they're living there and they're making their shell. And so they are super abundant in the sediment record. So if you were to take a core in the ocean, you're looking for diatoms, and you can identify them based on their unique and easily identifiable shapes. So here you can see ones that are round, ones that are linear, ones that are more triangle shape or square. And so they're easily identifiable. And they respond to changes in the environment. So they respond to the clarity of the water, the temperature of the water, the depth of the water. So we can learn a whole lot about paleo or ancient ocean conditions from looking at diatoms. But what we're considering here is that they're so abundant. So you can like statistically make great analysis looking at diatoms. And the rate at which they will preserve then in the fossil record is more likely because they are statistically more abundant. Another example would be some of the limestone pieces that we've looked at also in laboratory, where you see all these shells incorporated into a limestone or a coquina. And so you can tell that there's many of them that were living and then eventually dying in that situation. So they become more statistically abundant, and we can learn a whole lot about them in their natural environment, which is different than a vertebrate because they're going to be limited. And so I just show you a picture of T-Rex, because who doesn't love T-Rex, right? So we see T-Rex over here on the right. And so there are these massive land reptiles that are moving, and because they are massive, they take more resources in order for them to live. So they're less statistically abundant. So when we talk about fossil preservation, we first need to think about the abundance of the population that we anticipate was living on the planet. And there's a difference between the invertebrate population and the vertebrate population. The next thing has to do with the time and the rate of burial. So if something is living in the natural environment and dies, and let's consider like a vertebrate. So you've got a vertebrate that's even like a cow or something that's living at modern day, and it's living and that dies. The first thing that's going to happen, right, is that it's going to be scavenged and pulled apart. So in that situation, those bones are probably going to decay rather fast, rather quickly, and never even make it into the fossil record. So that's different than if something is buried quickly in the environment where the bones are going to be placed in an environment without oxygen. So it's called an anoxic environment. Anoxic, an environment without oxygen. So if you ever get a chance to go to LA and you're tired of being on Rodeo Drive, one thing that you can do is you can head over to the La Brea tar pits. And at the La Brea tar pits, essentially what this is an oil seep. And during the Pleistocene, which was relatively cold, 1.8 million years ago, it was a glacial phase. There were things like woolly mammoths that were living in areas of California. I know that's hard to believe, but you have these fantastic and massive woolly mammoths that were living. And in this specific area where there was oil, the woolly mammoths probably thought that it was a pond of which they could wade, so like a body of water. And what they would do is they would move into those bodies of water, and because it was so viscous, had a high resistance to flow, right? It's oil. They couldn't remove themselves from that situation, so they would end up dying in place. So there's these fantastic reserves of the fossil record where we're looking at complete skeletons of woolly mammoths from about 1.8 million years ago. And they're preserved perfectly because they were buried quickly. And so here's an example of some bones that were stuck in that tar. And then we can also consider the ancient city of Pompeii. I put up for you a video about Pompeii, a documentary that's just fascinating. I hope you really enjoy watching that, and there'll be some questions about it for your quiz on the following day. So Pompeii occurred 79 AD. What you're looking at on the right is a picture of Mount Vesuvius before it erupted. So you see the city kind of reconstructed in front of it. So Mount Vesuvius is one of the biggest and baddest volcanoes on the planet. It's, of course, on a convergent plate boundary right there on the edge of the western coast of Italy. And in 79 AD, there was a major volcanic eruption, and it produced a whole lot of silica-rich ash. And you can tell that from this picture, because when you look on the picture on the left, what you're seeing are people that were essentially buried in place. But you can see the volcanic ash. It's light in color. It's felsic in color. So remember, that was a big indicator about explosive volcanic eruptions that happen on convergent plate boundaries. So when Mount Vesuvius erupted, it had enough energy to blow 1/3 of its top off. So it's a major boom eruption. 1/3 of its top disappears initially, and it produces a whole lot of silica ash, enough silica ash to bury an entire city, and many other cities likely within a 50-mile radius of the volcano. So it produces a whole lot of volcanic ash. The ancient city of Pompeii, I hope you get to visit. It's a world heritage site. And you can walk through the village of Pompeii, and you can see where people died in place. And they suspect that the volcano probably erupted at night, at like happy hour time, like about 5 o'clock, when people were getting done with work. And that's because the bars were full and some of the brothels were also full. So to take this back to fossil preservation and time and rate of burial, in Pompeii, we know that these people were buried very quickly. And we can tell that because of their positioning within the community. Hopefully what happened, and it's suspected that this eruption of Mount Vesuvius had a whole lot of sulfur dioxide gases, and that wafted out of the volcano and moved into the city. And so hopefully what happened was they essentially went to sleep from the sulfur dioxide and also the carbon monoxide, and then eventually was buried in place. So a tragedy that happened. What's interesting is that Mount Vesuvius at modern day is starting to see evidence of like coming back to life. So it had a really long repose or dormancy, and now it's coming back to where it's becoming more active. And the city around Mount Vesuvius has offered people $50,000 to move. So the problem is that there are many wine producing vineyards around the flanks of the volcano, and that makes sense because the soil is so fertile from these volcanic eruptions that have happened, and so people don't want to move, especially for $50,000. But they're trying to promote people to move away from that radius that is going to be hazardous, and eventually they'll have to probably evacuate if there is, and when there is, another major eruption activity. And this is one of my other favorite places in the world. This is Asphalt fossil beds in Nebraska. So when you think of Nebraska, you probably just think of cornfields, and it is a relatively flat state. But if you drive away from Lincoln out west, you end up again in the Nebraska sandhills. And so what these are paleo dunes that had formed off of the ancestral Rocky Mountains. So you end up with this hummocky landscape. And these asphalt fossil beds come from the Eocene about 30,000 years ago. And during that time, the the landscape was transitioning from the Pleistocene, so moving away from the Pleistocene. And as it was doing that, the environment was moving from a cold phase into a drier, warmer phase. And so you're moving away from glaciers into a savanna plain. So the area was able then to support animals that would live in the savanna. So what you're seeing here are skeletons of rhinos. So asphalt fossil beds that was just discovered in the 1990s by one of my professors there, who's a paleontologist. He found these buried rhino deposits. And so what had happened in this case was there's a volcano that's in Wyoming that became volcanically active. The ash moved and wafted across towards Nebraska. And again, it produced enough volcanic ash that it buried this this ecosystem in place. So you find several different types of rhinos, and you find like small rabbit type creatures, and there were very short horses called Eohippus horses that were buried within the asphalt fossil beds. So again, the time and rate of burial was very quick, and so the fossil preservation is fantastic. Our third line of fossil preservation, we always ask the question, how did it die? So what caused the thing to die in the natural environment? So did they get trapped in the La Brea tar pit, or did something kill it? This is a famous picture of from the fossil record. And if you look at it closely, it looks like there's two dinosaurs kind of like fighting to their death. So they're combating, and eventually they both neither one of them made it, so they both died. But we asked that question because we are curious as if a plague might have happened, or if something else happened in the natural environment. So when we look at fossil skeletons, especially for things like Triceratops, so you remember Triceratops with the big skull cavity, and it has one or two horns. So Triceratops is often found in the fossil record to have broken lower jaws. And that's thought because they're so top heavy when they walk that they would fall and they would collapse on themselves, breaking their lower jaws. And so that would impede them from being able to eat, right? So there's that. When we look at some evidences of skulls of T-Rex, they often look to be kind of like scarred up or have like bite marks. And so it's suspected that like if T-Rex were trying to attack a pack of like velociraptors, for example, you can see like places where the T-Rex has been bitten on their body. Maybe they got away, maybe they didn't, but at least they were, trying to defend off T-Rex. Probably not enough to kill it, but you often just kind of look at the skeletal features to ask questions about how it died, because that again would lead to fossil preservation. So did it die quickly, where something attacked it and it died, or is it dying slowly, where it can go into maybe like a cave or a cavity and slowly pass away and then become part of the fossil record? And then based on how it died, we ask the question, what comes after death? So again, is it going to be very quickly, or is something going to come and scavenge it? And if something comes and scavenges it after its death, then those bones are going to be pulled away. So for example, if a major predator killed something, they would eat until they were full, they would leave the carcass, and then other things would come to feed off of it and eventually pull it apart. So that's going to become important, because when we look at the skeletal record, we usually don't find complete skeletons. They're usually disassembled in some capacity, and that probably is why we ask the question, what comes after death in the natural environment? And then the last thing we talk about is the durability of hard parts. So when we look for a fossil and we look for things like a skeleton, it's very rare to find one that's complete. Like, that just doesn't usually happen. Instead, you find the presence of things that have harder parts that are more likely. So we can consider teeth for an example. And I'm sure all of you have been to the beach and you've been into the stores, and you find the necklaces that have the fossils, or the modern examples of shark teeth. So teeth are something that's really super durable, and that can become incorporated into the fossil record. So you find an abundance. Also, things like sharks, right, regenerate their teeth over their lifetime, so they're abundant. You don't usually find a complete skeleton. Instead, you find pieces. So the other things that you often find are ribs. Often you find vertebra. Pieces of the pelvis are common. Oftentimes you find the upper skull cavity. You usually don't find the lower skull cavity. Metatarsals, so pieces of jointing, is often found. Kneecaps are often found. So things that are much more rigid. So it's less likely to find, like, you might find the humerus, but you might not find the radius and ulna, and that's just because they're smaller and less durable type of bones. Oftentimes you find the femur. Less common, you'll find the fibia and tibia. And it's important for you to know this. So, like, when you go to a natural history museum, or you're watching Discovery Channel or National Geographic, and they're showing you examples of skeletons, usually the skeletons are not complete. And usually what they've had to do is either bring in bones of other skeletons that are found in the area, so like piecing together to make a complete product, or they're having to anticipate what those bony parts might have looked like. So kind of like filling in and recreating, like there's an artistry to it to anticipate what you think those bones would have looked like. So again, like, and hopefully what can happen is that over time, other discoveries are made, and so you're filling in the geologic gaps. So you might not have the left femur to a T-Rex, but maybe eventually by 2022, somebody will find a left femur. And so then you can make comparisons and adjustments. And I think that's really exciting. And that's where some of the modern discussions come about, like are dinosaurs warm-blooded? Did they have feathers? And that comes from new discoveries where we begin to ask and question what we have understood in the past by filling in those geologic gaps. Here's a really good example on the screen. So you can see the amount of bones that was collected on the left, and then the finished product on the right. So what you anticipate it to look like, and what you actually find. So in addition, for it to be really hard to become a fossil, you might not find a complete fossil. And if you do, that's super exciting. And here's an example of a T-Rex, one of our favorite dinosaurs with those little arms. This is Sue. Sue's at the University of Pennsylvania Natural History Museum. Sue is thought to be one of the biggest T-Rexes ever found. And in November of last year, they found a T-Rex that's about 3 times bigger. So again, overcoming geologic gaps. So those are the 5 main things that we note or discuss when we're thinking in terms of fossils and how fossils are preserved. And then we are going to talk about a few other things that need to be considered. Just again to remind you, when we talk about the fossil record, we are thinking only in terms of sedimentary rocks. Now, we could find a metamorphic rock that contains a fossil, and I think I even showed this to you in lab, where you can have a piece of limestone and you add heat and pressure and it turns into marble. And so sometimes marble has evidence of fossils, but they're just kind of like squished and compacted. So that can happen, but where they are buried is going to be, and where they originate is going to be in a sedimentary type of rock. So whether that's going to be a sandstone, a limestone is super common. Coal, where you can find evidence of plants, are common. So they're usually sedimentary types of rocks. I suppose when we talk in terms of asphalt fossil beds or Pompeii, those are volcanic eruptions that are anomalous, that have produced enough ash to bury those fossils in place. So we can talk in terms a little bit about igneous formation and contributions to the fossil record, but not usually. Another limitation, again, has to do with the amount of species that actually make it into the fossil record. So to date, there's only about 250,000 species that have been defined for the past 570 million years. So a very small portion of what we anticipate living on the planet has been identified in the fossil record. Although we like to talk about vertebrates, they're truly scarce in the fossil record, especially with complete skeletons, for all the reasons that we've talked about. And so instead, we often look for the invertebrate record to give us clues as to how the environment was changing and responding. And you'll remember this term, unconformity, from when we talked about stratigraphy, remembering that you can have erosion that happens. So an unconformity is a gap in the fossil record where you have erosion. And so even if those fossils had made it into the stratigraphy, sometimes they can be destroyed, unfortunately. And we will sum it up with saying that less than 10% of all living vertebrates will become fossils. And as we explore the uprising of life in the fossil record, where we started the Precambrian 4.6 billion years ago, we'll notice and have to pay a lot of attention to the invertebrate record, because that's where the motions of life are first going to be found. And so it's going to be pretty exciting to be able to explore with you over the course and remainder of the semester. And I'll leave you with this slide, because this is the direction we'll go for the next lecture, where we're going to explore how fossils become part of the fossil record. So we talked about how fossils can be preserved, but now we're going to talk about the types of fossils that we can find. And so that includes unaltered remains, petrification or recrystallization, carbonization, impressions, and molds and casts. And this is truly exciting, because when we think of fossils, usually I think before you come into geology, you think that the only thing you can have is maybe a piece of petrified wood or a type of bone or tooth. But we're going to look at lots of different ways that fossils can be preserved and formed. So I'm going to stop here. You've been a wonderful audience. Thank you for your time, and I look forward to seeing you again.